Green's theorem. In vector calculus, Green's theorem relates a line integral around a simple closed curve C to a double integral over the region R bounded by the C. In Green's theorem, it must be a simple closed curve, and the question can be given in terms of scalar or vector function. This is an example of simple closed curve and piecewise smooth. So the purple color is the region, and this is a smooth curve. Piecewise smooth means that there is no hole in between the curve. For example, this one. This is not piecewise smooth because there is a hole in between the curve. So how to determine the positively oriented or negatively oriented? It depends on the arrow. If the arrow shows counterclockwise, that means positively oriented, and if the arrow is shown to the clockwise, it means negatively oriented. So for Green's theorem equation, we can write like this picture. So if you can see here, there is a circle at the integral over the C. That means the Green's theorem. P dx plus q dy is equal to double integral over R for derivative q with respect to x minus derivative p with respect to y dA. Or we can use the second equation. So the difference between these two equations is here. For the first equation, we write p dx plus q dy, and the second equation, we write p dy minus q dx. How to know which one from these two equations that we need to use is by referring to the arrow along the curve. If the arrow shows counterclockwise, which is positively oriented, then we need to use the first equation. If the arrow shows clockwise, which is negatively oriented, then we need to use the second equation. So we will discuss some example for better understanding.
Question number 1. The question asks us to evaluate 2x, x plus y dx plus x squared plus xy plus y squared dy over a contour C around the square with vertices at 0, 0, 1, 0, 1, 1, and 0, 1. First, we look at the contour, which is a square with a 4 corner, which is look like this: 0, 0, 1, 0, 1, 1, and 0, 1. The movement of the contour is like this, so it is in a positive because it's anti-clockwise. The movement of the contour is anti-clockwise, and C is actually simple. C is a simple closed curve because the endpoint and the beginning point is the same, which is here. According to the Green's theorem, integral of C p dx plus q dy is actually double integral of a dq over dx minus dp over dy dx dy. So in this type of equation, we need to figure out our p first and q. Later, we need to find the derivative of dq over dx and dp over dy. We need to find our p and q based on the question. So here is the question. We know that this is our p dx, and this is our q dy. So we have found our p and q, which p is 2x x plus y, which we which is 2x squared plus 2xy, and our q is x squared plus xy plus y squared. So we need to find our derivative of dp and dy. So dp over dy, we treat it as a constant, so we get our dp over dy is 2x here, and next dq over dx. So we treat y as a constant, and we get our dq over dx is 2x plus y. Dx is 2x plus y. After we get the value of dq over dx and dp over dy, we need to substitute the value, and here we got it. So actually we can simplify here is dy dx dy. The next step is we need to find our limit of for x, and the outer is our limit for y. So the limit is determined by the equation here, the square, which vertices 0 0 1 0 1 1 and 0 1. So the limit for our x is 0 to 1, and for y is 0 to 1. So we substitute the value 0 1 0 1 y dx dy. Okay, so we solve this 0 1 y x dy 0 to 1, and we will get the value is 1 y, still the same, because if we substitute the 0 and 1, we will still got y. Later here is equals to y squared over 2 0 1. We got the value is 1 over 2 here. So the answer for this question is 1 over 2. Thank you.
For this question, the equation states a particle starts at -2, 0 and moves along the x-axis to 2, 0. Then it moves along the upper part of the circle, x squared plus y squared equals to 4, back to 2, 0. Compute the work done on this particle by the force field Fxy equals to x cubed plus 3xy squared. So the first step we need to do is, based on the question, we know that the region will be bounded by the upper part of a circle x squared plus y squared equals to 4. So the diagram will be like this. A circle with a region bounded by the upper part of the circle with a radius equals to 2. And the direction will be a positive orientation. The next step is based on the function given fxy equals to x cubed plus 3xy squared, we can identify our p and q, and we can find the derivatives for p with respect of y and q with respect of x. So our p is equals to x, and q is equals to x cubed plus 3xy squared. So our partial derivative of p is with respect of y equals to 0, and a partial derivative of q with respect of x equals to 3x squared plus 3y squared. And then the next step is, as we know, the formula for work done is w equals to double integration f dr. So we can get our equation is w equals to double integration with, uh, with the function 3x squared plus 3y squared. So for this equation, we can use polar coordinates since the graph is a circle. So we can use the second equation, which is x squared plus y squared equals to r squared. So we can change the so we have our w equals to double integration 3x squared plus y squared dA. So we can change the equation with double integration 3r squared times r drt theta. Our limit for r is the the value of r that we get, which is 0 to 2, and our limit for theta is 0 to pi, since we have a hemicircle at the graph. And then we can know that from the equation we can use the normal integration. So we solve for the dr part, so we can get 3 over 4 r power of 4, and then it will be equals to integration of 0 to pi 12 d theta. And then we can integrate the 12, and it will be 12 theta pi j. J is a joule for a unit for work done.
Question 3. By using Green's theorem, evaluate the Green's theorem x power of 2y dx plus x power of 2y power of 3 dy, where C is the triangle with vertices 0, 0, 1, 0 and 1, 2 with positive orientation. First step, form a triangular curve based on a vertices given from 0, 0 to 1, 0, here 0, 0 to 1, 0, and then from 1, 0 to a 1, 2, and from 1, 2 to a 0, 0. So you can see this is a positive rotation where it's rotate anti-clockwise. So from this graph, we also can get the value of gradients, which is we get y is equal to 2x. And from this graph also, we can find the limits for dy and also dx. So for dy's, we make a one line here from 0 to this gradient, and we get 0 to x. For dx limits here from 1 is from 0 to 1 here. Second step, apply the Green's theorem. As we know, C is a positive orientation, which is rotate anti-clockwise. So we are using this formula, Green's theorem, P dx plus Q dy equal to double integral over R, derivative Q over derivative x minus derivative P over derivative y dA. And then next, we have to find the P and also the Q from the equation. So the P will represent the x power of 2y dx, and Q will represent the x power of 2y power of 3 dy. And here we get P x power of 2y and Q x power of 2y power of 3. Next, we have to differentiate the y in P. So we get the x2, and in Q we have to differentiate in terms of x. So we get here 2x y power of 3. Third step, substitute the value inside the formula. So we're using double integral over R, derivative Q over derivative x minus derivative P over derivative y dA, and here we get the equation, and this limit we get from the sketch clearly. And then we convert to a dy dx, and the limits we get here for dy is 0 to 2x and dx is 0 to 1. As usual, we integrate the into of dy first. So we integrate the y, and we substitute the value of 2x and 0 inside the y. So here's the calculation here, and these are the answer for integrate the value of dy. 8x power of 5 minus 2x power of 3 dx. And same goes for this step. We have to integrate in term of x. So at x power of 6 over 6 minus 2x power of 4 over 4, and the limit is 1 and 0. As usual, we substitute 1 and 0 inside the x. So here are the calculation, and then we get the answer here, 5 over 6. Thank you for watching.